Okay, guys, welcome back to this week's lecture. This week we'll be talking about physics of solids, liquids, and gases. And looking at the title, you may be thinking like this is an extremely vague and general title, and that's because actually this week's lecture is just, for the most part, it's just going through mostly physics 1 and physical chemistry, and just finishing up on the things that we haven't covered in depth yet. And it's just a mix of things that are pretty much all over the place. And this is kind of like mostly it's focused on solids, liquids, and gases, but it's such a broad topic that it really focuses on a lot of different parts of chemistry. Again, this is my information with my email if you ever want to contact me. I recommend joining the GroupMe if you haven't already. Learning objectives for today. So first we're going to be talking about what are the mechanics and mechanical advantages of different systems. And we're going to be focusing more on the mechanics, which is like the first thing you learn in physics. Next, we'll be talking about what are equations diagrams used for thermodynamic systems. We'll be focusing on like the physical chemistry and the thermodynamics, especially when it comes to gases. Okay. And actually, that's the next thing. What are some physical chemistry laws related to gases, relating pressure, volume, moles, temperature, things like that. And lastly, we'll finish off with what are some fluid concepts and how do they relate to our circulatory system. So fluids are an important part of physics, and more so they're important in biology because we have fluids in our body, and that's how our circulatory system works. Okay. All right, moving on to the content. First is mechanics. First, we're going to talk about conservative forces. First, we want to talk about the different categories of forces. Biggest categorization is conservative versus non-conservative forces. For a conservative force, the path the force takes on an object does not affect the work done by that force. But in a non-conservative force, it does. So some examples of conservative forces are electric force, gravitational force, elastic force. And other examples of non-conservative force are like friction, applied force, tension. What does this mean? Well, what it means is whenever you apply a force on an object, or a force is applied to an object, that force does work on the object. What conservative forces means is that no matter what the force, like which path the force takes, whether it takes this red straight line, whether it takes this curvy green line, or this blue path from point A to point B, doesn't matter. The work done is the same regardless of which path you take. Whereas obviously, if, for example, applied force is a non-conservative force. Applied force is when you like push something. So if you took object A right here, and then you pushed it to point B using this red path, that would you would be exerting a certain amount of work. You'd be doing a certain amount of work on object A, right? Well, if you, instead of pushing the object down the red path, if you instead pushed the same object A, this way on the green path, and you did all of these unnecessary curls and whatever to get to path B, you'd be actually doing a different amount of work, right? It, obviously, as you would expect, be a little bit harder, and you'd be actually doing more work on the object in order to get it to move, because you're actually moving longer distance. Same thing with if you took path C. So a non-conservative force like the applied force, or like the tension on a string, or like friction, it depends which path you take to get from A to B. Whereas something like gravity, it doesn't matter which way you go, it's the same amount of work being done regardless. Okay, so that's just an important distinction. Next, we want to talk about point-object systems. A point-object system is any system where the object we are looking at is represented basically by a point in space. And you've been using point-object systems probably without knowing it in physics your entire college and high school career. And the reason is because when, for example, if we were to find the total energy of an apple mid-fall from a tree, well, if it's falling, you know that what energies are acting on it. Obviously, it has kinetic energy because it's moving. It has a velocity, so it has kinetic energy, and it has height, so it has a potential energy, right? That's what makes up its energy. So you would just draw a diagram, kind of like here. I'll draw it. The apple's right here. It's falling down from a tree. It has a certain, here's the ground, has a certain height. The object has a certain mass and has a certain velocity as it's going down. Things like that. G is 9.8, whatever, right? And notice how in this drawing, I drew the apple as a dot, a point, right? That's because if I drew it instead like this, like everything is like a real apple, right? Then you kind of have to figure out like, okay, does it maybe rotate a little bit as it's falling? And where's the center of mass located? How does the shape affect the way it falls? Maybe the shape gives it some rotational energy, or maybe like slows it down or something like that. Maybe there's some kind of other factors in play if it's like apple shaped, right? So to make things simpler, we just treated any object, no matter what it is, like an apple, a water bottle, anything, a car. We usually treat it as just a point in space, like a single point, right? And we don't take into account that like the shape. So if it was like a car, we don't take into the shape and like where its center of mass would be. How does its like aerodynamics affect it or something like that, right? That just makes it a lot more complicated than we can solve. And so one way that we actually, like in real life, when you're doing physics and you're doing like models, like maybe in MATLAB or in some kind of CADing program, you'll obviously have to work with like real objects, and you'll have to find all this information out. But for the MCAT, it doesn't matter. If like for simple physics, we just use point objects, okay? Next, going off along that, we also have to learn about its center of mass. For simple objects like a sphere, center of mass is exactly the middle of the sphere, right? Makes sense? As long as it's like a uniform sphere, it's in the middle. But for more complex objects in systems, that's not the case. Like, for example, I have a water bottle here. What's the center of mass in the water bottle? It's not going to be exactly in the middle of the water bottle. It'll be somewhere else, especially in this water bottle where it's only half filled, right? If I put it like this, it's a different center of mass. And if you have a car or like a person, right, it's a different center of mass. So in a system that has multiple masses, right, the equation is as follows. And this equation doesn't come up too often, but this is the equation for center of mass. So x center of mass, cm is center of mass. So the location of x is like the location. The location for the center of mass is equal to the mass of object 1 times the location of object 1, mass of object 2, location of object 2, and then so on, mass 3, location 4, whatever, right? And then all of that divided by mass 1 plus mass 2, mass 3, mass 4, whatever, as it goes on, okay? Let me show you a picture of that. This is what like a simple system of masses would look like. You have this one small mass right here, this big mass right here, and you have to find the center of mass. Well, the x is the location, like I said. So the location of the center of mass, location of 1 times m1, location of 2 times m2, and you do this formula, and then you find the center of mass somewhere here, right? You can see it's not exactly in the middle between them, but because they're different masses or something, right? Yeah, this is probably as much as you'll see on the MCATs, like simple points, again, points, and that have masses. That's how you make a system to get a center mass of a system. In real life, if you had something like a water bottle or like an apple, what you would do is you would pick different points on like the apple or on the water bottle, like a bunch of different points, and you'd have an algorithm that determines the center of mass between all of those different points. And it's like kind of like a integral, and you can use actually integrals to find the center of mass of an object like that as well. But most programs have like a built-in algorithm for that, and you'll just have a system with many different masses in like a water bottle, and then using all of those, it'll kind of construct where the center of mass of a water bottle or a person is. Okay, but I really doubt they'll ask something like that. Most they'll ask is like simple points like this. Okay. Next, we're moving on to the work kinetic energy theorem. This theorem is used to relate net work to the change in kinetic energy. The equation is net work equals 1/2 mv squared final minus 1/2 mv squared initial, right? So essentially, this can be rewritten as, write it here, work equals delta KE, right? Work's essentially equal to the change in kinetic energy. That's what the network is equal to. If the network is positive, then the final velocity is greater than the initial velocity, and kinetic energy increases. If the network is negative, the kinetic energy decreases. Network is 0. There's no change in velocity, right? Because mass of the object, assumedly from the start to finish, stays the same. 1/2 is 1/2, and then the only variable is v. Very simple. Just remember, work and kinetic energy are very closely related using the equation work equals delta KE. Okay. Last thing we want to talk about for mechanics is mechanical advantage. So we often in real life use tools to do work for us that would be impossible otherwise. Like for example, we use levers or pulleys, which we can put minimal or lower amounts of force into, but they yield a much higher force on the other end, right? If you had like a car jack, you obviously can't lift a car, but if you just press down on the car jack, it can actually lift up the car enough, right? Because it's a lever system, and when you press on it, it can output much more force than you can input. And this is called a mechanical advantage. There are 6 simple machines that we are used for mechanical advantage: levers, inclines, pulleys, wedges, screws, and wheel and axle. They each have their own formulas, which you don't have to know, in terms of how they kind of like convert things. Like mostly usually it's based on like length and things like that. That for like wheel and axle, like diameter, and like it has a lot of different things. That's way too specific and too complicated for the MCAT, so you don't have to know them. But the formula that you should know is that mechanical advantage is a ratio of output to input. Thus, mechanical advantage is equal force out, O is for output, over force in, or input, right? So however much force you get out divided by how much you put in, that's the mechanical advantage of the certain machine or system. There's just a diagram of what it looks like a lever, obviously like a seesaw, or like a car jack, something like that. Pulleys, screws, obviously wheel and axle, inclined plane, wedges, right here. Okay, now let's move on to thermodynamics. Okay. First, we're going to start off with heat transfer. So there are 3 methods of heat transfer. I think this is the most important part of like thermodynamics for the MCAT that you really have to know. Conduction, convection, and radiation. Conduction is direct heat transfer from physical contact. Example, you touch a hot frying pan. Touch a hot frying pan, the heat goes from the frying pan directly into your skin, right, by direct contact. Next is convection. This transfers from a surface to a fluid, and it results in the subsequent movement of the fluid as a result of being heated. Note, this is via a fluid, not a liquid. So convection can occur through gases as well, not just liquids. Okay. For example, water being boiled in a pot. The heat goes directly from the very hot pot directly into the water, which is a fluid or a liquid. And the liquid, it ends up moving a lot in the pot. As a result, the water molecules end up moving a lot. So the hot ones go to the top, whereas the colder ones rise, and then they get heated up, and then it's just a cycle of movement. Okay. And then lastly is radiation, which is no direct transfer required. It transfers energy via transfers thermal energy via electromagnetic waves through space. For example, a campfire just emits heat. You don't need to touch the fire. You don't need to have like any kind of fluid necessarily, although the fireplace will also heat the air around because it is fluid, but like the actual fire itself is not physical, it's not a surface. So it transfers heat through electromagnetic waves. It's the fire is not an object, right? You can't really touch fire because it's not really an object, it's more like an energy, right? And this is just a graph showing this. Conduction is directly touching a stove. Convection is you heat the water from the pot, the bottom of the pot heats the water, and then the hot air rises, warm air falls, and then it just goes in a cycle. And lastly, radiation is just a campfire or something like that. It's transferring heat through electromagnetic radiation, right? Next up is state versus path functions. Chemistry, there's state and path functions, which are properties very similar to conservative and non-conservative forces, in that state functions are properties that do not change based on the path taken to get to the value. For example, change in pressure, volume, temperature, enthalpy, entropy. And these are properties that are innate to the process. For example, if you turn water into ice, right? The pressure, the volume, whatever, it doesn't matter how you turn the water into ice, it'll be the same. The enthalpy, the entropy, Gibbs free energy, all of those don't change regardless of how you actually turn the water into ice, right? It's just the start point and the end point. Whereas path functions do change based on the path you take by the process. For example, heat and work. So there are some ways to turn water into ice that maybe use up a lot of heat, whereas other ways use up less heat. Some that require more work, some require less work. It depends on which path you take. Path functions are not properties of necessarily the process itself, but rather the steps taken, right? So heat is not a property of turning water into ice. It's a property of the specific way you turn the water into ice, right? Okay. Path functions, name implies, rely on the path. State functions are part of the state. They're not related to the path. Okay. Next, I know we're jumping through a lot of different topics. PV diagrams. So the PV diagram is kind of important, and I think it is important, especially as some important vocabulary that I think you should know. The PV diagram shows the relationship between pressure and volume for a certain system. So again, if we're talking about water to ice, it might, or like some kind of gas diagram, we might want to look at like this PV diagram for specific gases that are being used, and usually it's for gases, not liquids or solids. So yeah, as you can see here, there are 4 different types of reactions that you will probably see on a PV diagram: isobaric, isothermal, adiabatic, and isometric. What do all these mean? Well, isobaric is constant pressure, and if you look, pressure's on the y-axis. No matter how much you change the volume, the pressure is always going to be at this, which is like, for example, like 10. No matter what volume it is, it's always just going to be at 10 because it's constant pressure. Same thing with isometric, which is constant volume. Let's say this is like 3, right? These are just made up numbers, but yeah. No matter what the pressure is, the pressure can go up. The volume will still always be 3. Next is, these are a little more complicated, isothermal, which is constant temperature. This is what things like Celsius, Kelvin, Fahrenheit measure, temperature, right? Isothermal is temperature. Looks kind of like this, right? And then adiabatic, which is constant heat, which is not the same thing as constant pressure or constant temperature. Temperature and heat are 2 different things, and I think I covered that a little bit in the previous thermodynamics lecture, but I really recommend you knowing the differences between temperature and heat because they are not the same thing. Temperature is usually written as things like Q, right? Whereas temperature is written as like T, for example, but they're not the same thing. So constant temperature, constant heat, adiabatic, also looks kind of similar to isothermal, but like this. And these obviously change depending on the process. It's just like kind of like this is the trend, I guess, right? So adiabatic might be like here or like something like that, right? Or like here. But this is generally the shape it will be. And remember, the work done is always equal to the area under the curve. Again, just like integrals kind of, but you do kind of have to know a little bit of basic integrals for the MCAT, but like this, like for isobaric, this would be like the shaded region. So find the area under the curve, right? It's very simple. You just know how to find the area of like a square or rectangle. It's very easy. This is a little bit harder. Probably impossible actually, unless, yeah, impossible without like a calculator knowing the specific formula. So you wouldn't be asked to do something like this, but they might give you something like this isobaric, right? But just know that the work done is the area under the curve. And if you look here, isometric right here, you can't, how would you find the area under this curve, right? Well, you can't, right? And the area under this curve is nothing. It's like this. So it's actually like the area under this curve is 0. And that's because isometric processes, which are at constant volume, have a work of 0. And unless you change the volume, you're not actually doing work on a system of gases, right? Like the actual changing of volume is what determines whether or not you are or aren't doing work on the system. Okay. Next, let's talk about some important laws. Firstly is Boyle's law. It states that pressure and volume of a gas is inversely proportional under constant temperature. I'm going to explain what the law says, and then I'll show you what equation is derived from that law. Mainly what you really have to know is the equation, but it does help to know what the law states itself. So it states that the pressure and volume of a gas is inversely proportional under constant temperature. So P1 V1 equals P2 V2, right? I'm sure many of you knew that. Next up is Charles' law, which states that, and actually if you want to see this, you can see here that constant temperature, which is isothermal, this one, as the volume goes up, which is to this side, the pressure goes down, right? As the pressure goes up right here, the volume goes down, inversely proportional. So that is like a physical way to see Boyle's law. Next up is Charles' law, and which states that in an isobaric, which is a constant pressure process, volume and temperature will be proportional to each other. And the equation that we can derive from that is V1 over T1 equals V2 over T2. All right, very simple. And T, important to note, T is in Kelvin, not in Celsius. This needs to be in Kelvin, otherwise you might get a wrong answer. Okay? Because when you do things like if you are like kind of like doing ratios of like temperature to temperature, it doesn't matter. Like for example, if you did a change in temperature, sorry, not ratios in temperature, that matters. If you do like a delta T where it's a change in temperature, it doesn't matter because it's addition, subtraction. So it doesn't matter if you use Celsius or Kelvin. For multiplication and division, it does matter if you use Celsius or Kelvin because the numbers will be off. Next up is Avogadro's law, which states that in an isothermal and isobaric constant temperature and pressure process, volume and moles of a gas are proportional, right? So V1 over N1 equals V2 over N2, right? Really, mostly you just have to remember the equations, but it does help to remember the laws as well. Next up is Boltzmann's constant. The Boltzmann constant relates the kinetic energy of gas particles with the temperature of the gas. So, for example, the formula of Boltzmann constant equals PV over Tn, where N is the number of molecules of gas, not moles. Remember, molecules is moles with also taking into account Avogadro's number, multiplying by that. So the formula for Boltzmann constant is with molecules of gas, not moles of gas. And we know that the value of the constant is this, 1.38 times 10 to the negative 23. You don't have to memorize that, nor do you have to memorize the units. They will give you Boltzmann's, they should. I think I've always seen, if they ask for constant, I've always seen that they do give the value and the units of the constant, right? And they may ask you to find like P or find T or find V or something like that, right? And you just have to plug in the rest. Okay. So it would help mostly just to know this formula, right? Rather than the value of the constant. Okay, last thing for thermodynamics, I think, is coefficient of thermal expansion. This is a coefficient that is unique to each substance, and it is a measure of how much that substance expands per unit of temperature. The units of this coefficient are per degree Celsius, right? So this Celsius to the -1 is actually just 1 over Celsius, okay? And as you can see here, there's 2 alpha and beta. Don't worry about the difference between them. It's not too important. Just whatever one they give you, that's the one you use. Appropriate coefficients of thermal expansion for aluminum, concrete, diamond, glass, steel, and water. Obviously, if you have something like water, for each degree of heat or each degree of temperature that it changes by, it's going to get a lot bigger, a lot smaller compared to something like diamonds or like concrete, which doesn't get bigger or smaller really with temperature, right? Which, I mean, should make sense to you. Why something like a liquid does, and whereas a solid doesn't. Okay, last thing we're going to be covering today is fluids. I'm not even going to try and pronounce this guy's name. This guy's law. The law can be used to find the pressure difference when talking about a liquid flowing through a constantly sized pipe, like for example, a straw or your lung alveoli. Okay, so we use this formula, delta P equals 8 mu LQ over pi r to the fourth, where L is the length of the pipe, Q is the flow rate, R is the radius of the pipe, and mu is the viscosity, and P is delta change in pressure, right? And there's a lot of variables, and usually you won't have to like do all of these because this is a lot of math. Usually what they might ask you something like that is if you like double the length of the pipe, but you make it, but you have its rate, the radius of the pipe, how would that change the change in pressure? And then you would know that 1/2 would be to the fourth, whereas this would only be doubled, so it would you have to just do the math there. Okay. And like the answer would be like, it would be like 30 times bigger, like 10 times bigger, like 2 times bigger, 4 times bigger, 2 times smaller, something like that. Okay, and that's just like an example. All right, next we want to talk about laminar versus turbulent flow. What we typically think of for fluid flow is called laminar flow. And when I say typically think of, I mean in terms of physics. In terms of real life, we actually mostly know liquid flow as turbulent flow rather than laminar flow. And I'll show you an example in a bit. Laminar flow is when all of the fluid flows in a parallel lines with no flow just kind of disrupting each other. The fluid in the center flows the fastest and slows to get to the edges. I'll show you a diagram of what this looks like, but think of this like a flock of birds flying orderly together in like a V formation. So the liquid is kind of going in a V formation, and all of like the particles of water are staying in their own lane and kind of just going in a straight line, and they're all parallel to each other as well as parallel to the pipe. Okay. However, in real life at faster velocities or in other cases, like the ones that typically occur when you open your faucet, you actually get turbulent flow instead of laminar flow, which is chaotic and disorderly. And this is what I mean when I say in real life, you probably know turbulent flow. When you open up your faucet, the water that comes out is turbulent, it's not laminar. Turbulent flow is chaotic and disorderly. There is a lot of perpendicular movement and mixing between the lanes. This is more like a chaotic highway when there's like a lot of traffic. There's cars merging, changing lanes, cutting each other off constantly. It's kind of like very chaotic. It's not staying in a line. This is kind of what it looks like. So remember, laminar flow is kind of like the V shape, right? And each of these like a line of water molecules going straight, whereas turbulent flow has a lot of these like twisting and kind of like doing this and that, right? And there's like mixing and nothing is like orderly. Okay. And like I said, when you see, we'll be mostly working with laminar flow in physics, but in real life, actually most flow that you see is probably turbulent. If you opened your faucet and instead of turbulent flow, which is what water normally looks like, laminar flow would look like this, right? This water is actually supposed to be like moving, but you can't even see that it's flowing. It just looks very clear and very orderly, and that's because it's moving laminarly. Okay, this is what water would look like out of a laminar faucet. So let's talk about in our bodies. Generally in our bodies, blood flows laminarly. However, there are certain conditions in which it becomes turbulent. An important value to know is the Reynolds number. A high Reynolds number, usually about more than 2,300, is usually turbulent, while anything lower is laminar. No, Reynolds number is unitless because all the units cancel out. And the equation for Reynolds number is RE equals rho V D over mu. V is velocity, D is diameter, rho is density. don't get confused with the D's. One is density, the other is diameter. And mu is viscosity of the liquid. Our blood vessels typically have a very low diameter, so the D is very low. And because that, Reynolds number is also usually fairly low, and you get mostly laminar flow because the Reynolds number is low. In things like sometimes in our aorta, which is like thicker, you may get turbulent flow in that one area, right? And like there's a lot of research going into this, and there's like a lot of like models, like mathematical models and stuff that are being used to like show like the different change in flow and everything. You don't have to know that. I just know Reynolds number is important. This is the equation for it, which is important to know. Usually our body is laminar, sometimes turbulent. Okay. And that's it for today's lecture. I know there's a lot of things that we covered, from circulatory system, flow, these different laws, coefficients, thermodynamics, a lot of stuff we covered. So, but this hopefully helped fill in the gaps that were missing from our 15-week program when we talked about thermodynamics, mechanics, and liquids and gases and circulatory system, things like that. Hopefully this kind of helped kind of give you some clarifications on some stuff. Okay. All right. Thank you very much for joining us, and we'll see you guys next week. Bye.